All right, let's talk about something that is literally all around us, but is completely invisible. Think about it. The silent signals that carry our phone calls, the waves that heat up our lunch, and even the stuff that lets doctors see right inside our bodies. We're about to dive deep into the invisible code that powers our entire modern world.
So, to get started, here's a question for you. What in the world could your phone, a hospital x-ray machine, and the sun possibly have in common? I mean, they seem totally unrelated, right? But believe it or not, there's a powerful, fundamental force that connects them all. Any guesses?
And the answer is the electromagnetic spectrum. This is the one single concept that ties everything together, from the radio station you listen to in your car to the light you're using to see right now, and even to the super intense radiation coming from deep space. To really get it, we have to look way, way beyond the colors of the rainbow. Right, so we've all seen a rainbow. But that is just the tiniest sliver of what's really out there. So for this first part, we're going to pull back the curtain and take a look at the whole incredible picture. Okay, here it is in all its glory. Now, I know this looks a little complex, but just focus your eyes right in the middle. See that tiny little band of colors labeled visible? Yeah, that's it. That is everything the human eye has ever seen. Every color, every sunset, the light from your screen. As you can tell, it's a ridiculously small piece of the entire puzzle. To make sense of it all, scientists break the whole thing down into 7 main regions. You can think of it like a lineup, going from the most chill waves to the most energetic. We start with the really long, low-energy radio waves. Then we move up to microwaves, infrared, then there's our little slice of visible light, and then we get into the heavy hitters, ultraviolet, X-rays, and the most powerful of them all, gamma rays.
So, what really makes a radio wave different from a gamma ray? If they're all part of the same family, what changes? Well, it turns out they all play by a very clear set of rules. So let's get into the physics of it and see what makes them tick. At its very core, every single electromagnetic wave is this cool little dance between two things, an electric field and a magnetic one. Notice how they're waving or oscillating at perfect right angles to each other, and also at a right angle to the direction the wave is actually traveling. It's this beautiful, elegant structure that lets them travel for billions of miles through the total emptiness of space. So, what's the main difference between all these waves? It all comes down to a really simple trade-off. If you have a long, stretched-out wavelength, like a radio wave, you're going to have a low frequency and low energy. On the flip side, if you've got a super short, scrunched-up wavelength, like a gamma ray, you get a crazy high frequency and a ton of energy. One goes up, the others go down. It's that simple.
And this perfect relationship is captured in one beautiful, simple formula. The speed of a wave equals its frequency times its wavelength. Honestly, this little equation is the master key to unlocking everything we're about to do. Just burn it into your brain. Speed equals frequency times wavelength.
Now here's the magic ingredient, the secret sauce. Even though their wavelengths and frequencies are all over the place, in a vacuum, every single one of these waves travels at the exact same speed. And that speed is the speed of light. We're talking 300 million meters every second. It's just staggering. This constant, which we call C, is the one thing that unites the entire spectrum.
All right, theory time is officially over. Now we're going to take those rules and that master equation and actually put them to work. Let's see if we can crack the code on some real-world physics problems. Here we go, our first challenge. This is taken right from the textbook. We know that a certain red light has a wavelength of 650 nanometers. So the question is, what's its frequency? In other words, how many times is that wave actually wiggling up and down every single second? The process here is pretty straightforward. First things first, we just rearrange our master equation a little bit to solve for frequency. Step 2 is super important. You have to convert nanometers into meters so all our units match up. Then, for step 3, you just plug in the numbers and do the math. And the answer you get is 462 terahertz. Now, what does that even mean? It means the electric and magnetic fields in that little beam of red light are oscillating 462 trillion times every single second. Yeah, it's an absolutely mind-boggling number. Okay, let's flip it around. This time, we know the frequency of a medical X-ray. It's a whopping 2.0 times 10 to the 18th hertz. That's an even bigger number. So the challenge now is to figure out its wavelength. Using that same equation, just rearranged for wavelength this time,
we find the answer is just 0.15 nanometers. That is incredibly tiny, so incredibly short that these waves can pass right through soft things like skin and muscle, which is exactly why they are so useful in medicine.
Okay, so we've seen the theory, we've crunched the numbers. Now let's zoom back out and explore some of the amazing and totally essential ways we use these different waves in our everyday lives. And this is really just scratching the surface. We use the incredible energy of gamma rays to treat cancer. Your Bluetooth headphones and your Wi-Fi, both are using microwaves. That warmth you feel coming off a spotlight, that's infrared radiation. The fiber optic cables that power the internet use infrared too. And of course, we just talked about X-rays. The spectrum is literally woven into the fabric of modern life.
Okay, time for a little quickfire round to see if you've got this down. I'm going to throw a couple more questions at you from our source material. Let's see how you do.
First up, your microwave oven at home. It operates at a frequency of 8.0 gigahertz. Using our master equation, can you figure out the wavelength of those microwaves? The answer is 3.75 centimeters. And it turns out, this is a particularly good wavelength for being absorbed by water molecules, which is exactly how a microwave gets your food hot so efficiently. It's a pretty clever piece of engineering. All right, last one. And this one's a little different. We're not talking about wavelength or frequency anymore. We're talking about amplitude, which is basically the height of the wave. So if one light beam has waves that are 2.5 times taller than another's, how much brighter or more intense is it? And the answer is 6.25 times more intense. This is a super important relationship to remember. The intensity of a wave isn't just proportional to its amplitude, it's proportional to the amplitude squared. So a small increase in the height of the wave leads to a much, much bigger increase in its energy and intensity.
You know, we've come a long way. We started by seeing the world through just that tiny slit of visible light. And now, using our technology, our eyes can perceive the entire spectrum. We can map the universe in radio waves. We can hunt for black holes with X-rays. So I'll leave you with this final thought. Now that we're getting better and better at seeing the invisible, what truly profound mysteries are still out there, just waiting for us to discover them? Thanks for joining me.